My name is Pascal Poupart. In this module, I'm going to introduce maximum entropy reinforcement learning. This is an important topic that comes with some really interesting theory, and we're going to cover two important papers. So the first one is called Reinforcement Learning with Deep Energy-Based Policies, and it talks about the soft Q learning algorithm. The second paper is about soft Actor-Critic, and then this one introduces an important baseline that is currently used by many people. You might wonder, what exactly is maximum entropy reinforcement learning? So in this module, we're going to answer this question, but more specifically, we're also going to talk about why there are several implementations of important reinforcement learning baselines, for instance A2C PPO, that are adding an entropy regularizer. There's also a question about why maximizing entropy is desirable in reinforcement learning. And finally, you might wonder, what is the soft Actor-Critic algorithm that has become an important baseline? In reinforcement learning, we can optimize policies that are either deterministic or stochastic. Now, for the purpose of this module, because we're going to talk about maximum entropy reinforcement learning, I want to summarize the advantages for both, but I want to highlight especially the advantages for stochastic policies, because that's what we're going to work with when it comes to maximum entropy reinforcement learning. Now, historically, deterministic policies were preferred, in part because we know that there always exists an optimal policy that is deterministic. So then, based on this, we can restrict the search space only to deterministic policies, and that is a smaller search space than the space of stochastic policies. In addition, practitioners tend to prefer deterministic policies because that ensures reproducibility, and when you observe your agent, there's a good feeling, when it always executes the same action. But if it's a stochastic policy and it might execute different actions in the same state, then there's a feeling that, maybe it's not quite optimal, it doesn't quite know what it's doing, and it should try harder to find the best action so that it would just execute that. So practitioners tend to have a bias then for deterministic policies due to those reasons. If we look at stochastic policies, historically they were considered in large part because some algorithms need a continuous search space. So if you consider continuous optimization technique, all those techniques that are based on gradient descent, like policy gradient techniques, they need a search space that is continuous. If we have some deterministic actions, then we need to turn that into a continuous space, and one way of achieving this is simply to have probabilities over those actions, and since the probabilities are continuous, then we can do gradient descent or continuous optimization more generally. Now, this is a nice advantage to allow the applicability of some techniques, but it's not necessarily an advantage in a domain or for a task. But it turns out that there are some important advantages about stochastic policies for tasks, and perhaps a very important one here is the fact that stochastic policies tend to be more robust. So what this means is that if we consider that our agent is learning about the environment, therefore it doesn't know the environment precisely, it would be dangerous to always select the same action based on some data that it has observed, because if this data is noisy, let's say that those samples are not representative of really what the environment is like, then the agent would be misled in always choosing an action that is suboptimal. But if, on the other hand, it chooses an action according to some distribution, then that distribution needs to be good in general, which means that those actions need to be fairly reasonable despite what the environment might be like, and therefore it will generalize better and the policy overall will be more robust. Another advantage is regarding exploration. So when we have a stochastic policy, there is some natural exploration that is built in, but in contrast, for deterministic policies, then we have to add explicitly an exploration strategy, and that is often made to be stochastic, like epsilon greedy or Boltzmann exploration. So in the case of stochastic policies, then the importance of adding an exploration scheme is not as great. It's still desirable, but you can do a lot more without worrying too much about explicit exploration. Another advantage is that in some domains we might be training in a simulator with the goal of deploying into some real environment that is necessarily slightly different from the simulator. So in that case, we want our policy trained in the simulator to transfer well to the real environment. So again, if we have a policy that is deterministic and it exploits some properties of the simulator that are not reflected in the real environment, then those actions are going to be suboptimal and it's not going to work well. But a stochastic policy tends to be more robust and therefore will generalize better when it needs to transfer to the real world or some related environment. One last advantage that is quite important is with respect to local optima. So if we consider deterministic policies, it's possible that an agent might select to execute a sequence of actions because it's relatively good, but it hasn't discovered yet that there exists another sequence of action that is much better, in fact optimal. And in order to discover that, it will have to essentially undo its current sequence of action and switch over to this new sequence that is optimal. Now, to undo that sequence, that will probably mean that it will have to decrease its performance until it completely switches over to the new sequence. And as a result, it might decide not to do that because decreasing performance would be bad. Right? So in that sense, it might just get stuck into a local optima. But if we consider stochastic policies, even if it is mostly executing a certain sequence of action with high probability, there's a possibility that there's a small probability for several other sequences, including the optimal sequence. So now in order to switch to that optimal sequence, it just has to increase the probability of that sequence, decrease the probability of the other sequences, and this is something that can be done much more easily, and in fact without having to decrease performance before increasing it again. So this will often change the landscape in a way where there will be less or fewer local optima. Okay, so this summarizes what are some of the important advantages of stochastic policies, and maximum entropy reinforcement learning will help us to benefit from those advantages, and now we're going to see how that plays out. If we want to encourage stochasticity in policies, we can do this by considering a soft MDP. So if you recall, a standard MDP has some states, actions, a reward function, transition distribution, and discount factor. And then a soft MDP is essentially the same, but with a bonus added to the reward. So the reward normally just measures how good is a state-action pair, but now we're going to add a bonus that will be increasing with the amount of stochasticity that a policy has. So this bonus is going to be based on the entropy function. Here we're going to denote it by h. So h of pi is the entropy of pi, and we can think of this as a measure of stochasticity. Now we're going to have a trade-off between stochasticity and the amount of reward, and therefore we're going to introduce lambda as a weight that helps us determine how much emphasis we want to give on stochasticity versus the original rewards. Entropy is a measure of uncertainty that can reflect the amount of stochasticity in a policy. So on this slide, I'm showing you the formula for the function of entropy, as well as a little graph that shows how entropy varies with probabilities. Regarding the formula, there's an interesting interpretation that comes from information theory, where we can see that there's a sum of x p of x, so we can interpret that as an expectation, and then the minus log p of x can be thought as a number of bits. So here in information theory, we're trying to communicate, let's say, some samples, and then the more uncertainty there is, then the more bits are going to be required to communicate this sample or to encode this sample. So the idea is that entropy is essentially measuring an expected number of bits to communicate samples from a distribution, and the more uncertainty or the more stochasticity there is in this distribution, then the more bits are going to be required. So as a result, then it's a function that increases with uncertainty. When we look at the graph on the right, we can see that when the probability of x is 0, then there's no uncertainty and the entropy is also 0. Similarly, when p of x is equal to 1, then again there's no uncertainty, it's deterministic, so the entropy is 0. But then if we think of x as a binary variable, and let's say that p of x is 0.5, then we really have a uniform distribution, which is the distribution with the most uncertainty. And at 0.5, here we can see that the entropy is at its peak. So generally speaking, entropy is a function that can be defined with respect to any distribution, discrete distribution, continuous distribution, and it will have a concave shape with a peak where there's the most uncertainty. Let's have a look at the optimal policy for both standard and soft MDPs. For the standard MDP, the optimal policy is simply the one that maximizes the expected sum of discounted rewards. In the case of soft MDPs, it's similar, but here you see we have an entropy bonus term, so it's the policy that's going to maximize the expected discounted sum of reward plus entropy. It turns out that this optimal soft policy is also known under various names, and you will encounter it as simply the maximum entropy policy, or it could also be referred to as the entropy regularized policy. Let's compare the Q functions for standard and soft MDPs. In the case of standard MDPs, the Q function is the reward for the initial state action pair plus an expected sum of rewards when we follow that policy. In the case of a soft MDP, the Q function works in the same way, so we have the reward at the initial state action pair plus an expected sum of future rewards with the entropy bonus term. Now you'll notice that there is no entropy bonus term associated with the first reward, and that might be a little odd, but it makes sense because you see the initial state action pair are not determined by the policy, so the policy only determines actions after the first time step, so therefore we're going to apply the entropy bonus only after the first time step. It's also interesting to compare the greedy policies with respect to the Q function that arises in standard and soft MDPs. So for standard MDP, the greedy policy is really just the policy that selects the best action according to the Q function in each state. Now if there's a single action that is best for a state, then the policy will be naturally deterministic. In contrast, when we look at soft MDPs, the greedy policy will naturally be stochastic. Now to obtain this greedy policy, we're going to do a similar computation. So we're going to take an argmax with respect to policies, and here what we're maximizing is going to be the expected Q function with respect to the stochastic policy plus the entropy bonus term. Now this computation, this maximization, we'll notice later on that we can reformulate it in a way that corresponds to a softmax. So in neural network, there's a softmax operator that essentially takes some input, exponentiates it, and normalizes it. So here we'll show in a moment that we can do the same thing. So our greedy policy can be reformulated in a way where it does correspond to this softmax of the Q values divided by lambda. Another interesting thing to note is that when lambda goes to 0, then the softmax becomes a regular max. And here this should make sense because lambda is the weight that determines the importance of our entropy bonus term. So when lambda goes to 0, then we're essentially saying that there's no entropy bonus term and we really have a standard MDP. So it's natural that the softmax should then become a regular max, and in fact when you look at the formula for the softmax, if you make lambda go to 0, then you should be able to verify that the softmax indeed approaches the regular max. Let's derive how the greedy policy corresponds to a softmax policy. We're going to denote our objective by j pi of q, and if you recall, when we find the greedy policy, we are finding the policy that maximizes the expectation of the q function plus our entropy bonus term. Now we can rewrite this by noting that the entropy bonus term is really itself an expectation of the log of the policy. So we can pull out this expectation so that now we have the expectation of the q function minus lambda log of the policy. So with this objective, now we're going to maximize it and find what is our greedy policy. The objective, you'll notice that it is concave, and as a result there's a single global optimum, and then it will be sufficient for us to simply compute the derivative and set it to 0. So now let's have a look at the partial derivative. So if we take the derivative of j with respect to pi, then we'll get that it is equal to q minus lambda log of the policy plus 1. If we set the derivative to 0 and then we isolate pi, then we obtain the following expression. So our policy pi of a given s will be equal to the exponential of q divided by lambda minus 1. This minus 1 is really just a multiplicative factor, and we can ignore it since we're going to have to renormalize the policy anyway. So here then it means that this is proportional to the exponential of q divided by lambda. So now we're ready to write down what is our greedy policy. So the solution is this exponential of q divided by lambda normalized, and then that corresponds to the softmax function. So that shows that really our greedy policy is the softmax of q divided by lambda. You might wonder, what is the value function induced by the greedy policy? In the case of a standard MDP, the value function is simply the max of the q function with respect to actions. In the case of a soft MDP, we can compute something similar, although at the surface the expression looks quite different, but it is similar. So here the value function for a soft MDP would take the sum of the expectation of the q function with respect to the greedy policy, and because this is a greedy policy, it's a bit like a max, and then we would add to this as well the entropy bonus term of the greedy policy. Now it turns out that this expression can be reformulated, and we can show that it corresponds to a log sum exponential of the q function divided by lambda, and log sum exp is a common expression in the literature to approximate a max operator in a continuous way. So we can think of this log sum exp as really a continuous maximum of the q function. Now if we make lambda go to 0, then again that corresponds to removing the bonus entropy term, and then we should recover the standard MDP. So it turns out that indeed when we make lambda go to 0, then our continuous max operator just becomes a regular max, a hard max. Let's derive how the value function induced by the greedy policy of the q function corresponds to the continuous max of the q function. So first, recall that the value function is really just the expectation of the q function plus the entropy term. So then we can make use of our definition of the greedy policy as a softmax policy to essentially replace the q of SA by the log of pi plus the log of the summation of the exponential of q divided by lambda. After this, notice that the expectation with respect to A does not apply to our log sum x term since it does not include A, so we can simply pull it out of this expectation. Then the expectation of the log of the greedy policy is really just the negative of the entropy of the greedy policy, so we can cancel the two entropy term and we're left with lambda log sum x of q divided by lambda. So this expression, by definition, is our continuous max operator applied to the q function, and this concludes the derivation. We're now ready to define an algorithm called soft q-value iteration. This algorithm is really similar to value iteration, but it is applied to the q function instead of the value function, and it is also meant for soft MDPs instead of standard MDPs. The idea is that in value iteration for a standard MDP, we would take the sum of the reward plus an expectation of future reward at every update. Here we're going to do the same thing, but when we compute the expectation of the future reward, instead of taking a max of the q function, we'll take the continuous max of the soft q function. So essentially replacing the regular max operator by our new continuous max operator. And that's really the only difference. At the end, we end up with a q function, and then if we want to extract a policy out of that q function, then we can apply our softmax operator. So in other words, the softmax of the q function divided by lambda to get a greedy policy. It's also interesting to note that the q function that we converge to does satisfy a soft version of Bellman's equation. So this algorithm will converge in the sense that the q functions in two iterations will be identical or nearly identical, but let's say that they are identical, then we really obtain here a soft Bellman equation because we're going to have the q function that's equal to the reward function plus the discount factor times the expectation of the continuous max of the soft q function. Since our goal is to do reinforcement learning, we can derive a soft q-learning algorithm that is based on this soft q-value iteration. The idea is going to be to simply replace expectations by samples, and then we're going to represent the q function by a function approximator, and in most cases this is really just going to be a neural network. Now, because of the function approximator, we won't be able to do updates to the q function just based on temporal differences, but instead we'll want to do the updates based on gradient steps that are derived from the temporal differences. Here's some pseudocode for the soft q-learning algorithm. This is really just a sub-variant of DQN. So what I did is I took the DQN pseudocode, I copy-pasted it here, and what I've changed is only the red part. So really the code is almost identical. All that's changed is that the max operator has become a continuous max operator. So this reflects the fact that we are working with a soft MDP, and that's really the only change that's needed here. Q-learning is great, but it's not the state-of-the-art in many applications in practice. So actor-critic techniques tend to perform better in many cases than Q-learning. So an interesting question is, can we derive a soft actor-critic algorithm? And it turns out that the answer is yes. All we're going to have to do is define a critique in terms of a soft Q function, and then an actor that computes a greedy softmax policy. As a first step towards a soft actor-critic algorithm, let's define a soft policy iteration algorithm. So if you recall, actor-critic techniques are based on policy iteration in a sense that the actor is really computing an improvement to the policy, and then the critique is just evaluating the policy. So on this slide, I'm showing the pseudocode for a soft policy iteration technique, and this technique essentially alternates between policy evaluation and policy improvement. Now, to deal with a soft MDP, all we have to do for policy evaluation is to add an entropy bonus term whenever we encounter some rewards. So in the evaluation step, you see in red, I've added this entropy bonus term. For policy improvement, we normally compute a greedy policy, but instead of just taking the max of the Q function, we're going to take the softmax of the Q function divided by lambda. So this is again the main difference, and that together gives us immediately a soft policy iteration algorithm. For the next 4 slides, I'm going to demonstrate some important theoretical properties of soft policy iteration. If you're not interested in those derivations, just feel free to skip ahead, but if you're interested, keep on listening. When we look at policy iteration, there is an important property where we can show that the policies are improving monotonically at each iteration. In the same way, Theorem 1 is saying that soft policy iteration also enjoys this monotonic improvement in the sense that the Q function at every iteration will be increasing, and therefore the underlying policies are improving. Now, to demonstrate this, we first need to show the following inequality. So this inequality has an intuition, which is that the value of a policy pi I at the current iteration is less than the value of the greedy policy at the next iteration. So here recall that the value of a policy, here I mean the value function v of a policy, is simply the expectation of its Q function plus the entropy bonus term. So that's what we've got for the left-hand side of this inequality, and then the right-hand side is the same thing, the same expectation, but with respect to pi I plus 1, which is going to be our greedy policy. So it's the expectation of the Q function with respect to the greedy policy plus the entropy bonus term, so that corresponds to the value function of the greedy policy. So really what this inequality is saying is that when we change the current policy to a greedy policy with respect to the Q function, then the values increase, and that's going to be critical to the proof of our theorem. So in fact, once we have this inequality, then we can just use it to show that the Q functions are improving monotonically. Let's show the important inequality where the expectation of the Q function and the entropy term with respect to pi I is less than or equal to the same expectation with respect to pi I plus 1, which is the greedy policy. So as a first step in this derivation, we're going to use the fact that pi I plus 1 is a greedy policy and therefore defined as a softmax policy. So what we do is we take Q soft of SA and replace that by lambda log of pi I plus 1 minus lambda log of the sum of the exponential of Q of SA prime divided by lambda. Then after this, we are going to bring together the two log of pi I plus 1 and log of pi I terms together into a single term of log of pi I plus 1 divided by pi I. Then we notice that the expectation of pi I log of pi I plus 1 divided by pi I is really just the negative of the KL divergence between the policies pi I plus 1 and pi I. Now since KL divergence is always positive, if we drop the negative of the KL divergence, then we end up with a larger expression. At this point, you'll notice that our log sum of exponential does not depend on A. It depends here on A prime but not A. So as a result, our expectation of pi I of A given S, we can change that to be an expectation with respect to pi I plus 1. So here changing the distribution of the expectation doesn't matter because it's not being applied to the rest of the log sum x term, so it's simply an expectation on its own that always sums up to 1, and therefore we can replace it by another distribution, so pi I can be changed to pi I plus 1. At this point, we can use again our definition that pi I plus 1 is a greedy policy that corresponds to a softmax policy to replace our log sum x term by q minus lambda log of pi I plus 1. And then finally, we can rewrite this to be our expectation of the q function with respect to the greedy policy pi I plus 1 plus our bonus term, the entropy of pi I plus 1. So this concludes the derivation of this inequality. We can now proceed with the proof that the q function increases monotonically. So first recall that the q function is simply the reward plus an expectation of future reward in terms of the q function plus our bonus entropy term. Then we apply the inequality that we just derived, which allows us to replace the expectation with respect to pi I by an expectation with respect to pi I plus 1, which gives us a larger or higher expression. Then after this, we take the q pi I that remains in the expression, and then we apply the same derivation over and over and over, which expands the expression, always creating larger and larger expressions, and then in the limit, this corresponds to q pi I plus 1. So in other words, this demonstrates that the q function increases from one iteration to the next. We can show a second theorem that says that soft policy iteration converges to optimal q functions and policies. This will be only in the case when epsilon is equal to 0. When our convergence threshold epsilon is close to 0, naturally here we're going to get policies and q functions that are near optimal but not necessarily optimal. Okay, so the first step for this proof is to take advantage of theorem 1, where we already showed that the q function is increasing monotonically. Now if it increases monotonically, an interesting question is, will it converge to something? And the answer is yes, as long as the q functions are upper bounded. So I'm showing you an upper bound, which is finite, and this upper bound is constructed by taking the maximum reward that can be obtained in any state action pair, plus the maximum entropy that any policy could obtain. That usually corresponds to the uniform policy because it has the most uncertainty. And then we would add this at every step while discounting. Now with the discount factor, we're really doing a geometric sum, and that would correspond to taking this maximum reward plus maximum entropy divided by 1 minus the discount factor. Alright, so this confirms that the q functions will converge, and then at convergence, the q functions are going to be equal, and then what this really means is that they satisfy Bellman's equation. Now if they satisfy Bellman's equation, then they are optimal, so we have an optimal q function, and that means that the greedy policy that is used at every step is also optimal. We're now ready to define the soft actor-critique algorithm. This is really going to be an RL version of soft policy iteration, where the idea is that we're going to use a neural net to represent the policy and the value function. Now when we use a neural network to represent the policy, we won't be able to update the policy directly just by taking a softmax, and instead we'll want to also project it back into the space of parameterized neural networks. So we're going to see in a moment that we can do this simply by minimizing the KL divergence between our softmax policy and then the neural network that has the closest parameterization to that softmax policy. Here's a pseudocode for the soft actor-critique algorithm. What I've done is that I modified the pseudocode for the soft Q-learning algorithm and turned it into a soft actor-critique algorithm. The changes are highlighted in red, and as you can see, there's not so many changes. So the first important thing conceptually is that with soft actor-critique we have an actor, and therefore we're representing a policy explicitly. In a case of Q-learning, there would be no policy. So at the beginning of the loop, we have a line where we sample an action according to a policy. So this is something new because we have a policy. In the context of Q-learning, we would simply select an action according to some heuristic, most likely some type of exploration heuristic. Here we can use the fact that our policy is stochastic to induce a certain amount of exploration, but obviously we could further modify this to also do some explicit exploration. In any case, a simple base version of soft Actor-Critic would just sample the next action based on the current policy. The second difference arises in the Q update. So the critique, which encodes the Q function, when it gets updated, we don't have to take the continuous max of the Q function in the temporal difference. So normally for Q-learning, you see the temporal difference is the difference between our current Q estimate and then the reward plus the continuous max of the soft Q estimate. The idea is that this continuous max of the soft Q estimate is really an expectation of the Q function with respect to the greedy policy. So since this is an expectation, we can approximate it by taking a single sample. So we're going to do a one sample approximation. And this has the benefit that if we have lots of actions or a continuous action space, then we'll be able to apply this algorithm. So in this case, I'm showing just a one sample approximation where I'm sampling A hat prime from my current policy, and then in the gradient calculation for the Q update, then I simply use that one sample. So that's how I get Q of S hat prime and A hat prime plus the bonus entropy term at S hat prime. The third change is the fact that now we have a policy to update because there's an actor, and the actor normally would correspond to a greedy policy, which is defined as a softmax policy, but because we have an explicit representation of policy in terms of a neural network, we need to project that softmax policy into the parameterization of the neural network. So one way of doing this is just to compute the KL divergence between the softmax policy and the neural network, and then to compute some gradient of that and take some steps to minimize the KL divergence. Alright, so this summarizes the changes with respect to Q-learning, but what's interesting is also to compare that to policy gradient techniques. And here what's really interesting is that even though this is an Actor-Critic technique, it does not do a regular policy gradient type of update. The update for the policy is by looking at the softmax policy and projecting it. Now this has an important advantage because then it allows us to do updates that are off policy. So normally in RL algorithms, if the updates are on policy, then we cannot use a replay buffer. But in the context of soft Actor-Critics, the replay buffer can be used simply because the update here is not dependent on the current policy, so it's an off-policy update that is based on just computing the softmax of the current Q function. So this is quite advantageous because we can use the replay buffer to replay some of our past experiences, and that can save in terms of the amount of data that is needed to learn a good policy. It also improves in terms of the stability. Let's compare empirically the soft Actor-Critic algorithm to soft Q-learning and a few other baselines. On this slide, I've got 6 robotic tasks, and for each task, the x-axis is the number of steps, the y-axis is the average return, which corresponds to the expected amount of reward that is earned. Now the key here is that we would like an algorithm that produces a curve that rises as quickly as possible. The soft actor-critic algorithm is in orange, and we can see that in 5 of the 6 tasks it does perform very well. In fact, it beats the other algorithms. Now when we compare soft actor-critic to soft Q-learning, which is in pink, it makes sense that soft actor-critic will perform better than soft Q-learning, simply because soft actor-critic is a form of modified policy iteration, whereas soft Q-learning is a form of just value iteration. So we know in general that modified policy iteration techniques tend to converge faster than value iteration techniques, and this gets reflected here. Another important aspect of soft actor-critic is that it uses a replay buffer, and therefore it has an advantage in comparison to other techniques that are policy gradient and therefore are on policy and cannot use a replay buffer. So for instance, the PPO algorithm is an example of that. So it is an on-policy algorithm that uses policy gradient updates, and it cannot use a replay buffer. So each time it must use some new data sample from the environment to do updates, and therefore it is less data efficient. To conclude this module, I encourage you to watch this video. We know that maximum entropy reinforcement learning techniques such as soft actor-critic and also soft Q-learning are adding an entropy term that essentially makes the policy more stochastic and therefore more robust. So this video shows us an interesting little robot called Minotaur, and it learns to walk quickly, and it also generalizes to environments that have some challenges that it wasn't trained to deal with. So this is pretty interesting to watch, and it clearly illustrates some of the advantages in terms of transfer learning and generalization.